This is a video going over the Unit 3 review materials. So everything we've done in Unit 3. So that includes imaginary numbers, complex numbers, solving quadratics with complex solutions with completing the square, using the quadratic formula, and all the work with parabolas that we did, all that focus and directrix stuff. So let's start off by looking at how to simplify some radicals when we have a negative under the radical. So for something like part A, radical negative 49, we can approach it the same way we approach a regular radical simplification. We ask ourselves what multiplies to negative 49 where one of them's a perfect square and one of them's not. Well, I know 49 already is a perfect square, so I can write 49 in one radical, and negative 1 times 49 would get me negative 49. So that just simplifies to 7, and remember that that radical negative 1 is defined as that imaginary unit I. So radical negative 49 turns into 7i. For part B, we can do the same thing, but notice that 200 isn't a perfect square yet. So if I'm thinking about factors of 200, I know 2 goes into it 100 times. I know 4 goes into it 50 times. But if I'm even looking at my factors, I know that 100's probably the biggest perfect square that can go into that. That's 10 times 10. So I'm going to stop there. So radical 100 times radical 2 would get me radical 200, but I want it to be negative. So I make sure to include that radical negative 1. So radical 100 is just 10. Radical 2, I. For negative 96, you could do the same thing where you're listing out all the factors, figuring out what's the biggest perfect square that goes into it. But for this one, it's going to be 6 and 16. If you want a quick way to figure that out, you could always go into your calculator and just go to the y equals screen, type in 96 over x, and just go to the table from there. And that'll give you all the factors of 96, and just look for those perfect squares. So I'm going to break it into negative 16, 6, and negative 1. So my final answer is 4 radical 6i. I always add that I to the end of my numbers because a lot of the times they tell me to put it in a plus bi form where that I is going to be at the end. Speaking of which, for the next problem, we have to leave all of these in a plus bi form. So we've got to remember a couple rules about I when we're looking at these problems. So before I do any of these problems, I like to write down the 4 different I terms that we kind of have to have in our back pocket here. I is just I. But I squared, if we're thinking about negative 1 under the radical times negative 1 under the radical, that's just, well, the radicals cancel, and we're left with negative 1. So that's negative 1. And now I cubed is just I squared times I, so we could rewrite that as negative I. And then I to the 4th is I squared times I squared, which is just negative 1 times negative 1, or positive 1. These are the only 4 forms of I you're going to need to know, because after this, if you look at something like I to the 5th, that just turns into I again, and then the pattern repeats. I, negative 1, negative I. So for something like part A, if I'm trying to simplify this 3 times I squared, I can replace as 3 times negative 1 plus 4. I know that I cubed is the same as negative I minus 2i plus 9. If I simplify a little bit, 4 times negative I is negative 4i minus 2i plus 9. And when I combine my like terms, I'm going to put my I terms in the back. So negative 4i minus 2i is negative 6i. and negative 3 plus 9 is 6. For part B, notice that I'm subtracting now instead of adding, and when I have parentheses with a subtraction sign in front of it, I need to distribute that negative to both of my terms. So it's like I'm subtracting the 2 and I'm subtracting the negative 8i, so that becomes positive 8i. From here I can combine like terms again, and I get negative 2 plus 12i. And this is an a plus bi form, remember, so the I term always needs to be in the back. For C, remember that something that looks like this are complex conjugates. And that's when you've got two of the same numbers, one with a plus and one with a minus in between. And if you remember, something good happens when we distribute this out. So if you remember how to distribute a binomial to a binomial, you do the first term times the first term, then the first term times the next term. 3 times negative 8i is negative 24i. Then I do my last term to my first term, plus 24i, and my last term to my other last term, minus 64, and then I times I, be careful with those exponents, is I squared. Now you should notice the middle terms here cancel. Negative 24i plus 24i is just 0. And you're left with 9 minus 64, and remember I squared is just negative 1. So this just turns into 9 plus 64, because a negative times a negative is positive, to get 73 as a final answer. D. Same process. I've got two binomials. I'm going to distribute. So 7 times negative 8, negative 56, plus 21i, plus 48i, minus 18i squared. Again, I'm going to combine like terms in the middle there. And remember, I squared is negative 1, so a negative times a negative is going to get me positive 18 for a final answer of negative 38 plus 69i. For E, even though it looks a little different than part D, it's actually a very similar problem. If I have a binomial squared, remember you've got to write it twice, and do that same process of distributing. Even though I've got a variable here, that y, all of my rules still hold true. I still multiply the first term to the first term to get 4. 2 times minus yi is minus 2yi. Minus yi times 2 is minus 2yi. And now a minus yi times a minus yi becomes positive y squared I squared. I can combine the like terms in the middle, and I squared times a y squared is negative y squared. And there's nothing really you could do here. You could put the I term in the back if you want to, but since the y is a variable, we could just leave it in this form, and that's fine. There's no more simplification you could do here because this is a y squared here, so that's not going to combine with the y term, and I've got a constant, so there's nothing more we could do here. For F, I've got one term outside the parentheses, and I've got two terms that I need to distribute it to inside the parentheses. Remember, the terms are separated by plus and minus signs, so I know there's nothing I need to do out here because everything's being multiplied. So I multiply the coefficients, or the numbers in front. 6 times negative 4 is negative 24. X times x is x squared, and I cubed times I to the first, remember when we're multiplying bases we add exponents, is just I to the fourth, plus 5 times 6 is 30, x I cubed. And then I remember my I rules. I know that I to the fourth is actually a really good one because that just simplifies to 1. So I've got negative 24x squared, and I know that I cubed turns into negative I. So I can put that negative on the outside here because a negative times this positive 30x, well, it's going to be negative 30xi. And again, these aren't like terms, so there's nothing more we could do here. Part G. This problem might look a little similar to the previous one, but notice that you've got this squared here. So I can't distribute that xi into my parentheses because if I'm thinking about my order of operations, the parentheses comes before the exponents. So I can't do anything with this. I can't multiply, that's even further down. So I'm gonna have to think about maybe doing something in here, or if I really wanted to, trying to deal with that exponent. But if I'm looking inside the parentheses, I minus 7i, those are both like terms. 1i minus 7i is just negative 6i. And now this looks like something we could deal with. So this is just xi 6i times negative 6i. Negative 6 times negative 6 is positive 36. I times I times I is I cubed, and I've got an x there. And again, remember that I cubed simplifies to just negative I. So your final answer is negative 36 xi. H. This one's a little bit more lengthy because you can see that we've got two binomials squared. So we're going to have to do that distributing process twice and then distribute that negative to my terms over here and combine like terms. So let's see what happens here. X times x is x squared plus 3xi plus 3xi. 3i times 3i is 9i squared, but remember I squared is just negative 1. So I'm just going to make that minus 9. Minus, in a big set of parentheses here, 2x times 2x is 4x squared, minus 6xi minus 6xi, and again, minus 3i times minus 3i is a positive 9i squared again, so I'm just going to make that a minus 9. And if I distribute my negative into my parentheses, remember that just means that I'm going to change all the signs. So x squared plus 3xi, or actually I can combine some like terms here first to clean that up a little bit. 6xi minus 9 minus 4x squared. I can combine this to a negative 12xi, and when I distribute that negative to it, it becomes positive 12xi. And when I distribute that negative to that negative 9, it becomes positive 9. I notice my 9's cancel. And I'm left with, when I combine like terms, negative 3x squared plus 18xi. Again, those aren't like terms. There's nothing more you could do there. Using the discriminant, determine the nature of the roots for each quadratic. Remember that the discriminant, when we're looking at the quadratic formula, x equals negative b plus or minus b squared minus 4ac all over 2a, that discriminant is just that number inside the parentheses there. So that b squared minus 4ac. So all I care about is what that number under the radical is, because that'll tell me if my roots are going to be rational. I know if it's negative, my roots are going to be imaginary. So let's start. For my first one, my a is going to be 5. My b is going to be negative 2. And my c is going to be positive 1. So when I plug into the formula for the discriminant, b squared minus 4ac, I get negative 2 squared minus 4 times 5 times 1. Don't forget those parentheses there. If you do forget them, your calculator doesn't know what to do with that negative, so a lot of the times you might get one of the wrong answers here. Okay, 2 squared is 4, minus 20 is going to be negative 16. Well, if I have a negative under the radical, let's think about what that would be in the quadratic formula. So I'd have that. That would simplify to 4 and negative 1. So that would end up being 4i. So I know I'm going to have some sort of imaginary part there. So these roots are going to be imaginary. For number 3, it asks for the roots of the equation again, but notice that my first one was in standard form, but this one isn't. So the first thing I need to do is try to get this quadratic into standard form. So I'm going to distribute that 4, and then I'm going to add 3x on both sides. So I write it as 4x squared, then my x term is 3x, and my constant is a minus 4. Now my quadratic's in standard form, and I could label an a b, and a c, and do the same thing I did for number 2. So b squared is going to be 3 squared minus 4a, and my c is negative 4. So 3 squared is 9. 4 times a negative 4 is negative 64 times a negative gets me positive 64. So this discriminant is 73. So I know it's not going to be imaginary. But if I'm thinking about when I get 73 under a radical, 73 is not a perfect square. So I'm not going to get an integer answer. It's going to be some sort of long, non-repeating decimal that's going to be irrational. So I can say that these roots are real, rational, and unequal. Remember, the only case where we do get equal roots is when our discriminant is equal to 0. So for number 4, very similar process. The only thing we need to do is subtract 9x on both sides first to get 2x squared minus 9x plus 4 equals 0. I label my a, my b, and my c, and I do the same thing. I'm looking at b squared minus 4ac. So negative 9 squared minus 4ac. 4 times 4 is 16, times 2 is 32. And 81 minus 32 is 49. If I'm looking at 49, I'm liking the way that looks, because if I take the square root of 49, I know that's just 7. So, in this case, I'm going to get rational roots because I have a perfect square as the discriminant. So, the question is it going to be equal or unequal? Well, if I think about the negative b plus 7 over 2a and negative b minus 7 over 2a, if I add 7 to something compared to subtracting 7 from something, that's going to change the answer. So I will get 2 distinct roots in this case. Solve by completing the square. Okay, if you don't remember the steps for solving by completing the square, I always like to get my quadratic in standard form first. It just makes it easier to deal with. So the first thing I do is move my c term to the other side. X squared minus 2x. I leave a space here, and I leave a space here. Now my next step is to take my b term, divide it by 2, square it, and add it to both sides. So notice that your b right here is negative 2. So if I take negative 2 divided by 2 and square it, well, that's just negative 1 squared. So that's just positive 1 that I'm going to add to both sides. So add a 1 here, add a 1 here. And the reason we do this is because it turns this left side into a perfect square trinomial. So you could do the process where you ask yourself what multiplies to positive 1 and what adds to negative 2. And that's negative 1 and negative 1. But a quick shortcut is to just look for whatever half of b was. That's going to be the number you put in the parentheses there. So negative 7 plus 1 is negative 6. When we take the square root on both sides, we're left with x minus 1 equals, remember when you take a square root to have that plus or minus there. And instead of writing radical negative 6, I'm going to pull that negative out of the radical and just make it an I, because I know when I have a negative under the radical, I'm going to have some sort of imaginary term. I add 1 to both sides, and I get x equals 1 plus or minus radical 6i. Part B. X squared minus 4x equals negative 13. In this case, I know my first step is going to be to move my c term to the other side, so I'm not even going to bother to move that 13 over because I'm just going to have to move it back over again anyway. So I do the same thing where I take half of b, square it, and add it to both sides. Negative 4 divided by 2 is negative 2, and negative 2 squared is positive 4. So I add a 4 here, and I add a 4 here. This left side factors into x minus 2 squared equals negative 9. And again, remember, if you don't know what to put in those parentheses, just look for whatever half of b was. Take the square root on both sides to get x minus 2 equals, now remember, if it's a negative under the radical, you could pull out an I. And 9's a perfect square, so the square root of 9 is just 3, but remember to have that plus or minus there. Add 2 to both sides, and you get x is equal to 2 plus or minus 3i. And again, always put that I term in the back because we want to leave it in a plus bi form. Part C. Again, notice that it's not in standard form yet, so you've got to do a little bit of distributing before you can start here. X times x is x squared minus 2x plus 2 equals 0. Move my c term over to get x squared minus 2x. I leave a space equals negative 2, and I leave a space. Half of negative 2 is negative 1. Negative 1 squared is positive 1, so that's what I'm going to add to both sides. And when I factor this left side, I'm left with x minus 1 squared equals negative 1. I do the same thing where I take the square root, and I get x minus 1 equals plus or minus, well, the square root of negative 1 is defined to be I, so that one's pretty simple. I add 1 to both sides, and I get x equals 1 plus or minus I. Now, D might look a little different than the ones we've done so far, but I claim the process is exactly the same once we do one thing. We normally have this x squared with a coefficient of 1 in the front, but I notice it's being divided by 4. To undo the division by 4, we can just multiply by 4 on both sides of the equal sign. Because what happens there is 4 divided by 4 is just 1, so you're just left with x squared on that side. And when I distribute this 4 on my right side of the equation, I get 4x minus 8. If I subtract the 4x on both sides, I'm left with x squared minus 4x, I'm going to leave a space, equals negative 8, and I'm going to leave a space. Half of negative 4 is negative 2, and negative 2 squared is positive 4. So I can add 4 to this side, add 4 to this side. This factors into x minus 2 squared equals negative 4. And again, I'm liking that negative 4 because I know it's a perfect square. So when I'm looking at this right side of the equal sign, that just simplifies to, well, the square root of 4 is 2, and since it's negative, I know there needs to be an I there. Add 2 on both sides, and we get that x is equal to 2 plus or minus 2i. Solve using the quadratic formula. Remember, in order to use that quadratic formula, we need to get our quadratics into standard form first. So I'm going to distribute that 8 on this side to get x squared plus 1 equals 8x minus 24. Subtract 8x and add 24 on both sides, and we get x squared minus 8x. 1 plus 24 is 25, and now it's equal to 0. So that's in standard form. I can identify an A, a B, and a C, and start plugging into the quadratic formula. So, x equals negative 8 plus or minus the square root of negative 8 squared, notice those parentheses I have around the negative 8 there, times 4, my A is 1, and my C is 25. All over 2 times 1. So a negative 8 becomes positive 8, and under the radical, I'm left with 64 minus 4 times 25 is 100. So I'm left with a negative 36 under the radical there, times 2, or divided by 2. I can simplify further to get 8 plus or minus 6i divided by 2, which once I divide both of my terms by 2, I get x equals 4 plus 3i, and x equals 4 minus 3i. My work for part B is going to look very similar to my work for part A. Once you get it into standard form, the process works exactly the same. X equals, my B term is negative 10, plus or minus the square root of B squared, plus or minus the square root of B squared minus 4, my A is 1, and my C is 41. All over 2 times 1. X equals a negative 10 becomes positive 10, plus or minus, well, 4 times 41 is 164, so it's 100 minus 164, so I'm left with negative 64 inside the radical here, all over 2. And again, negative 64 is something I want to see there, because I know 64 is a perfect square. So I could just make that 8i, and again I'm dividing by 2. So from here, I can split it off and divide both my terms by 2 to get x equals 5 plus 4i, and x equals 5 minus 4i. Number 7. Solve each system by substitution. So remember, substitution is when we solve for one variable and then plug it in for the other. So neither of these say y equals or x equals yet. So I'm going to take this top equation and try to get it to say y equals. So if I subtract 2x on both sides, I get negative y equals 4 minus 2x. And then if I divide by negative 1 on both sides, I get y equals negative 4 plus 2x, which I can rewrite as y equals 2x minus 4. I know sometimes it's kind of hard to look at in that form, so I try to get into my habit of writing my x terms first. So what I'm going to do is I'm going to take this value for y and plug it in for that y right there. So what that looks like is x plus 3 squared plus, instead of y, I'm going to write 2x minus 4 squared equals 25. I've got two binomials squared. I could write both of them twice and distribute. So x plus 3 times x plus 3 plus 2x minus 4 times 2x minus 4. These system problems, when it's a quadratic and a linear, are normally pretty lengthy because there's a lot of distributing to do. So just make sure that you're being careful with all your minus signs and all your distributing. Plus 2x times 2x is 4x squared, minus 8x, minus 8x, negative 4 times a negative 4 is positive 16, equals 25. Whew. Okay, so I'm looking for some like terms to combine. I got these x squareds here, so I can make that 5x squared. And then I've got 3x, 3x is 6x, minus 16x is going to get me minus 10x. And then I've got 9 and 16, which makes plus 25. And that is equal to 25. Okay, well this is looking pretty good because when I subtract 25 on both sides of the equation, I get 5x squared minus 10x is equal to 0. So this might be done easiest by factoring. I won't need to complete the square or use the quadratic formula here. So if I'm looking at 5x squared and minus 10x, I notice they both have a 5 in common, and they both have an x in common as well. So when I factor that out, what I'm left with inside the parentheses is just x minus 2. I can set both parts equal to 0, 5x equals 0, and x minus 2 equals 0. Divide by 5 on both sides, I get x equals 0 as my first x value solution, and x equals positive 2 as my next solution. Once you have your x values, plug them back into whatever equation is easiest to work with. So I could plug into this form of the equation if I want to, but notice that we already solved for y here. So it's probably going to be easiest just to plug back into that. So one of my y values, when I plug in 0 for x, is just going to be y equals negative 4. And my other y value, when I plug in 2 for x, 2 times 2 is 4, 4 minus 4 is 0. So my other y value is 0. So you could leave your answer like this, but remember, these points represent the points of intersection of that line and that circle. So I'm just going to leave my answer as in a couple ordered pairs. So when I plugged in 0, I got negative 4, and when I plugged in 2, I got 0. So that would be my solution. Both are perfectly acceptable answers, though. For part B, I could still do this by substitution, and I notice that both of them are already solved for y. So I can just take this value for y here and plug it in for that y right there. So I get negative 2x plus 1 is equal to negative 2x squared plus 3x plus 1. Anytime I have a quadratic, I always try to get it equal to 0. So I add 2x on both sides, subtract 1 on both sides, and I get 0 equals negative 2x squared plus 5x. And the 1's cancel. So I could try to factor here and see what happens. It looks like between the negative 2 and the 5 there's nothing I could pull out, but they do have an x in common. When I pull that out, I'm left with negative 2x plus 5. So I could do the same thing I did for the last problem, where I split it off and set both parts equal to 0. And you get x equals 0. This is already solved for you. But notice there's a little bit of algebra you've got to do on this side first. Now, even though you're not getting an integer solution here, that's still okay. So negative 5 divided by negative 2 is going to be a positive 5 over 2, or 2.5. I'm going to leave it as 2.5, just because when I plug it back in, I think that might be easier to deal with. So, again, I'm going to pick whatever equation's easiest to work with. So y equals negative 2 times 0 plus 1. So y equals 1 is one of my y value solutions. And y equals negative 2 times 2.5 plus 1. Negative 2 times 2.5, well, 2 times 2.5 is 5, so that must be negative 5 plus 1, or y is equal to negative 4. Again, you could leave your answer as a pair of ordered pairs. When you plugged in 0, you got 1, and when you plugged in 2.5, you got negative 4. So those represents the coordinates where my two graphs intersect. Number 8. A parabola has its focus at 1, 2, and its directrix at y equals negative 2. What is the equation of the parabola? Right, well, the focus is 1, comma 2, so right there. And the directrix is -2. So if I go down 2 and draw a horizontal line from there. So even in my head, before I figure out where the vertex is or what the equation is, I know my parabola is going to open upwards and the vertex is going to be somewhere in between there. Remember that the vertex is just halfway between the focus and the directrix. So notice that there are 4 units between them. So if I just go down 2 units from the focus, I can see that my vertex is going to be at 1, 0. And remember that those x values are always going to be the same. Okay, so I have that. The only other piece of information I need to find the equation is the focal length. And remember, that's just the distance between the vertex and the focus. So it looks like that's 2 units there. So when I'm looking at my formula for the vertex form of a parabola, 1 over 4p times x minus h squared plus k, where h comma k is just the coordinates of the vertex there, and p is the focal length. So as I'm plugging in, I get 1 over 4 times 2 is 8, x minus 1 squared, and now my y-coordinate of my vertex is 0, so if I add 0 to anything, a number, an equation, it's not going to change the value. So I'm just going to leave that part off. So this would be what my final answer looks like here. So if I go to sketch it, my parabola is just going to look something like this. Number 9. Given the parabola in vertex form, y equals 1/12 times x minus 2 quantity squared plus 2, what are the coordinates of the vertex? Well, remember that this looks something like our vertex form for a parabola, where h comma k is our vertex. So it looks like 2 comma 2 would be the vertex of this parabola. So I'm going to plot that. Over 2, up 2. There's my vertex. What is the focal length? Remember, the focal length is represented by that p next to the 4 there. Well, if I'm looking for similarities between these two equations, it looks like instead of a 4p, there's a 12 in that denominator there. So if I plugged in 3 for p, 3 times 4 would be 12, so I'm going to say that p is equal to 3 in this case. And now, what are the coordinates? That should say focus. So what are the coordinates of the focus? Well, it either could be above my vertex by 3 units, 1, 2, 3, or it could be below my vertex, 1, 2, 3, by 3 units, depending on which way this parabola is opening. Remember that the focus is always in the interior of the parabola. And I notice that my leading coefficient here is positive, so it's going to open upwards. So I know this point right up here is going to be the coordinate of my focus. So that's going to be 2, 1, 2, 3, 4, 5. What's the equation of the directrix? Well, that's a y equals line because it's a horizontal line. If I went up 3 to find the focus, I go down 3 to find the directrix there. So that's just going to be at y equals -1. Alright, so I sketched it with the focus on the interior of the parabola opening away from the directrix, so I know this picture matches this equation. And you could always plug into y equals into your calculator just to check. Number 10. Which equation represents the set of points equidistant from the line and point R shown on the graph? So remember, equidistant means that it's equal distance between the two things. That's actually the definition of a parabola. The locus of points equidistant from a fixed point and a fixed line. So if I'm looking at this, remember it's halfway between the focus and the directrix to find the vertex. So 1, 2, 3, 4. So I'm just going to go up 2 to find that my vertex is probably at 2, -1. And the focal length, the distance between the vertex and the focus, is going to be 2 units. So my p-value is 2. So there's a couple questions you need to ask yourself here. Does it open upwards or downwards? And I know it needs to open away from the directrix, so I know it goes downwards. Let's see if that eliminates any answer choices. Nope, they're all -1/8. So I know even knowing the focal length won't help me out here. So I just need to plug into the vertex form of a parabola that says y equals 1 over 4p times x minus h squared plus k. So my h value is 2, so it's going to be x minus 2 squared, and my k value is -1. So if I'm adding a -1, that's the same thing as subtracting a 1. So negative, because it opens downwards, 1/8 x minus 2 squared minus 1. So that's just going to be answer choice 4. Number 11. What is the equation of the directrix for the parabola -8 times y minus 3 equals x plus 4 squared? Notice that this parabola looks a little bit different than the ones we've had in all the previous examples because it's not solved for y. Not a big deal for us. We can use a little bit of algebra skills to solve for y here. Divide by 8 to get that to cancel. And you're left with my y minus 3 equals... Now, I could write this as x plus 4 squared over -8. But I'm going to pull that -8 out into the front. Because remember, dividing by a number is the same as multiplying by 1 divided by that number. Okay, from here I could add 3 on both sides. Notice it's already starting to take shape to look something like the vertex form of a parabola. And I get y equals -1/8 times x plus 4 quantity squared plus 3. So this is an equivalent form as this, but it might be a little bit more useful to us. So it says, what is the equation for the directrix for this parabola? Well, you need to identify a couple things here. I know my p-value is going to be 2, because I know that the beginning of the equation goes 1 over 4p. So if instead of 4p I've got this 8 down here, I know the p had to be, I know the p had to be 2 to plug in there. I know the p had to be 2 to plug in there. So I know my vertex is at -4, +3, because I see a +4 and a +3 there. So I'm going to just sketch a picture. Doesn't have to be perfect. Alright, so -4, +3 means left 4 and up 3, so somewhere over there. And I know this parabola opens downwards because it has a negative leading coefficient, that -1/8 out in front. So I know my directrix has to be somewhere above that parabola. So if my vertex is all the way up at +3, I know it can't be y equals 1, y equals -6, or y equals -2. My only option is that it's y equals +5. Reason being, if my focal length is 2, I can just go up 2 units to figure out what my directrix was. If I wanted to figure out what my focus was, I could just go down 2 units from my vertex. Number 12. Which equation represents a parabola with the focus at 0, 1 and the directrix of y equals -1? So first thing right off the bat, I made a typo. Instead of -47, that's supposed to be -4y. Not sure if that helps us, just something to keep in mind. Okay, so I'm gonna sketch what they're telling me here. Say I've got a focus at 0, 1, so if I go up 1, there's my focus. And the directrix is at y equals -1. So if I go down 1 unit and draw a horizontal line there, that's going to be where my directrix is. So something like right about there. And again, this is just a rough sketch, doesn't need to be perfect. So they tell me nothing more. So I've got to be able to deduce something from here. I know my vertex is going to be halfway in between these two objects. So let's see, if there's 1 unit between there and another 1 unit between there, then if I go down 1 unit from my focus, which is at 0, 1, I can get down to my vertex, which is going to be 0, 0. Now remember that when the parabola opens up, it can't go through the directrix, so it's going to need to open upwards here. So I know that I'm going to have a positive leading coefficient, so I can rule 1 and 3 right out. The problem is, though, even if I could figure out, well, my focal length or my p-value is 1, these two equations aren't solved for y yet. So if I divide 8 on both sides for answer choice 2, I get y equals 1/8 x squared, and for answer choice 4, I get y equals 1/4 x squared. So the question is it going to be the one with the 8 in the denominator or with the 4 in the denominator? Well, if I'm thinking about that 1/4p x minus h squared plus k, I'm thinking about what number did they plug in for p to get that denominator. For this number 2, it looks like p had to have been 2, and for this one right here, p would have had to have been 1. In our example, our focal length is 1 because the distance between the vertex and the focus is 1, and the distance between the vertex and the directrix is also 1. So your final answer choice is number 4. So even though none of these answer choices looked like the equations we're used to working with, we can still solve them for y and apply our same knowledge of that formula.